All right, and what I presume will be our last video for this series, for Chapter 7, we're going to talk about percent yield. Okay, we've already talked about theoretical yield. Okay, and theoretical yield is the amount of product which can be produced. Okay, that's the important thing, that can be produced based on the amount of limiting reagent. Okay, the actual yield is the amount actually obtained in a laboratory setting. Okay, because in real life, in real laboratories, things get spilled, measurements are inaccurate, people make mistakes, humidity's wrong, pressure's wrong, who knows? Lots of things happen to limit the amount that you actually get when you do an experiment. So in these images here, the images on the left is a chocolate factory. Okay, and you see all of the many containers that are making chocolate. And you may only get one bowl of actual chocolate out of all of that work. Okay, so what's important for you to know is that the actual yield will always be given. Okay, that's given information. That's never something that you can calculate because it's all based on real life, actual circumstances. Okay. So let's take a look at a problem, 32a. So a chemist carries out the following reaction beginning with 5.25 grams of magnesium carbonate. And we've looked at this particular reaction before. After the reaction is complete, 2.37 grams of magnesium carbonate or magnesium oxide are actually obtained. What was the theoretical yield of magnesium oxide? Okay, so first we're going to calculate the theoretical yield. Okay, so we start with 5.25 grams of magnesium carbonate. Okay, and we've dealt with this particular reaction in a previous video, so I'm not going to go back and go through the process of calculating the molar mass of magnesium carbonate. Okay, but suffice to say that if I need to go from magnesium carbonate to magnesium oxide, I need to use a mole ratio. So my first task is to get to moles. So I'm going to use molar mass, and it was 84.32 grams of magnesium carbonate per mole. That's the molar mass of magnesium carbonate. And again, just as a refresher, we calculate the molar mass of magnesium, 1 carbon, 3 oxygens, and comes out to be 84.32. Now that I'm in moles of magnesium carbonate, I'm going to go to moles of magnesium oxide. Okay, so 1 mole of magnesium oxide, and I'm going to put magnesium carbonate on the bottom because I want that to go away. Okay, so my moles of magnesium carbonate will cancel. So if I stopped here, I would have moles of magnesium oxide. Okay, but I want to get to grams of magnesium oxide because my actual yield is in grams. Okay, so let's use molar mass to go from moles of magnesium oxide to grams of magnesium oxide. And in the previous video, we figured out that the molar mass is 40.31 grams of magnesium oxide per mole of magnesium oxide. Right, so we find out that our theoretical yield is 2.51 grams of magnesium oxide. And so let's take a look at 32b. Right, so the chemist carries out this reaction with that given amount, and after the reaction is complete, we have 2.37 grams of magnesium oxide obtained. That's the actual yield. Okay, what is the percent yield of magnesium oxide? So percent yield is actual divided by theoretical times 100. Okay, so our actual yield is 2.37 grams. Our theoretical yield was 2.51 grams times 100 means that our percent yield is 94.4%. Right, so I encourage you to give this video a pause, see if you can work out the problem yourself, and then come back. Okay, so given the following reaction, using 2.03 grams of iron and excess sulfur, okay, that's important information. Excess sulfur means that the iron is the limiting reagent or the limiting reactant. Okay, when you're told that one of your reactants is excess, that means that the one you're given is limiting, and will tell you the theoretical yield. Okay, so from the balanced equation, the chemist calculates they should obtain, they should obtain 3.2 grams of iron sulfide. Okay, however, they only isolate 2.5 grams of product. What is her percent yield? Okay, so they calculate they should obtain, all right? They calculate they should obtain 3.2 grams of iron sulfide. That's your theoretical. Okay, however, she only isolates 2.5 grams of product. That's your actual. Okay, so percent yield equals actual over theoretical times 100. So our actual yield was 2.5 grams. Our theoretical was 3.2 grams times 100. So we should get a calculation of 78.1% yield. Okay, again, give the video a pause, see if you can work it out on your own, and then come back and see how you did. Okay, so starting with 14.2 grams of, what is that, hexane maybe? C6H6, and an excess of Br2. So excess of Br2, that tells us that the C6H6 is limiting. Okay, and will tell us the theoretical yield of the reaction. A chemist isolates 13.7 grams of C6H5Br. What is the percent yield for this reaction? Okay, so looking at our reaction here, and we are wanting to go from C6H6 to C6H5Br. Okay, so this 13.7 grams, that's the actual yield. Okay, so we need theoretical yield. Right, so since I know that the Br2 is excess, I can calculate the yield just from the amount of C6H6. Right, so we need grams of both, right? Because we're given grams of C6H6 and grams of C6H5Br, so we need molar mass of both. So the molar mass of C6H6 is 78.12 grams per mole. Okay, remembering 6 times 12.01 for the carbon, 6 times 1.01 for the hydrogen. Add those together and we get 78.12 grams per mole. Our molar mass of C6H5Br, 6 times carbon, 5 times hydrogen, and 1 times bromine, gets us a molar mass of 157.01 grams per mole. Okay, so I'm going from C6H6 to C6H5Br. Okay, so I'm going to go through moles, or through grams to get to moles, use a mole ratio, and then back through grams to finally get grams of C6H5Br. Okay, so grams to moles, C6H6, then to moles, C6H5Br, then to grams of C6H5Br. Okay, I need that grams of C6H5Br in order to calculate the percent yield. All right, so we start with 14.2 grams C6H6. Convert that to moles. Right, so I'm going to put grams on the bottom so the grams go away. So 78.12 grams of C6H6 per mole. Right, and notice throughout all of the problems, through all of these videos, I'm being very careful to label everything very clearly. That way I can track my work and I can make sure that things are canceling the way they're supposed to. So grams of C6H6 will go away. If I stopped here, I would have an answer that is moles of C6H6. Now I want to convert to moles of C6H5Br. And it's a 1-to-1 ratio. I'm going to put C6H6 on the bottom, C6H5Br on the top. That way my moles of C6H6 will cancel out. So if I stopped here, I would have moles of C6H5Br. But in order to calculate my percent yield, I need grams. Okay, so I'm going to convert moles of C6H5Br to grams. I'm going to put grams on top so that they stay. And moles on the bottom so that they cancel out. Okay, now I'm unfortunately kind of out of space on this slide, so I'm going to erase a few things real quick. Okay. So my theoretical yield is the result of this equation, and we find that we get 28.5 grams of C6H5Br. Right, now my percent yield is actual over theoretical times 100. Remember, our actual yield is this 13.7 grams. Okay, so we have 13.7 grams divided by the theoretical yield, 28.5 grams, times 100, gives us a percent yield of 48.1%. And it sounds like it's kind of low, but it's actually quite typical for this type of reaction. And I think this a little bit of an extra slide. Okay, so here we are at the end of the Chapter 7 slides. There are no speed drills for this particular set of slides, which may make you wish for more, in which case there's the textbook problems, or you may typically ignore those, and that's fine. Okay, enjoy your knowledge of stoichiometry and limiting reactants.